SwayamPrabha. Digital India. Educated India.
As you will see in reference 32 given at the end, various researchers have been developing models to study abrasive jet micromachining process in terms of erosion rate or material removal rate, and they have tried to compare the predicted results with the experimental results also in some cases. Now, here if you see carefully, this is the nozzle dimensions given over here in terms of measure. Now, here they have compared level nozzle and cylindrical nozzle as I have shown you in the earlier slide. Now, this is the distribution of the abrasive particles in the level nozzle modeled, and this is the distribution in case of cylindrical nozzle. Now, you can clearly see the difference. Here there is a concentration in the center and thin distribution of the abrasive particle out of the center, while in this particular case it is a uniform distribution. Thus, the shape of the nozzle is going to affect the distribution of the abrasive particles across the cross section of the exit nozzle, exit cross section of the nozzle, that you can clearly see here. And here it is the particle count. Now, as you can see here, it is more uniform in this particular zone and little deviation is there in the rest of the zone, but here it is more of parabolic nature, something like this. So, here you will find that concentration is there in the center. So, and thinness is there on the outer side. So, the cavity shape will be just reverse of this particular shape, while this shape can be something like this also. So, it gives you more uniform shape in this particular case compared to the cylindrical nozzle. So, you can see particle count, nozzle width, across the width also you find particles more or less uniformly distributed, except the end parts. Here you can see these two end part, three end part. Here distribution is thin, but in the center more or less the same, but in this particular case it is something like a parabolic one. So, the cavity shape that you are going to get in all these two cases will be quite different, and that is what the researchers in reference 32 have tried to analyze it. Modeled particle dispersion and jet expansion after leaving the nozzle. Now, you can clearly see this is again modeled results, not actual photographs. This has been done theoretically. Here also you can clearly see that this is the circular nozzle, cylindrical kind of the pipe kind of the thing, and again as we have seen in the earlier slide, there is a concentration in the center and thinness of distribution of the abrasive particles on the two ends, that and this is increasing as the nozzle tip distance increases 0, 2, 4, 6. I have shown you in the earlier slides also that as the nozzle tip distance increases beyond 0.5 millimeter or 1 millimeter, then flaring of the nozzle takes place, and this is showing flaring of the nozzle like this as the nozzle tip distance increases, and also the distribution of the abrasive particle is changing. Similar, more or less a similar kind of phenomena is observed in case of level nozzle, except that in the beginning as well as at the near to the end, the distribution is comparatively more uniform as compared to cylindrical nozzle, as you can see here, this compared to this and this compared to this at the same nozzle tip distance or stand-off distance. So, this shows you clearly that in this particular case, in the case of level nozzle, you will get comparatively straight sided cavity, while in this particular case you in the case of cylindrical nozzle you will get tapered type of the sides of the machined feature or machined cavity. That is the main difference between the two because of the distribution of the abrasive particles in these cases. So, you can see the cross sections here as well as here, both are shown over there. So, measured axial velocity profiles of both ends. Now, this is very interesting one, as I have mentioned in the earlier slides also. Similar kind of the things is seen over here. Nozzle width is given over here from the center on the left side as well as on the right side, and this is the average particle velocity. Now, you can see here maximum velocity you can find in the center. That is why you have the tapered cavity in this particular case, because on the sides or at the other end of the nozzle the velocity is very small. So, the cavity depth is also very small and it is increasing as you move towards the center. So, you have the tapered cavity machined by this particular nozzle, that is the cylindrical nozzle. But if you see the level nozzle, here the taperedness is not as serious as in this particular case, and in all the 4 cases, although at the as you go deeper and deeper probably some kind of taperedness is coming over, some more taperedness is coming over here, but in rest of the cases that taperedness is not so serious. So, we can clearly say that in case of level nozzle more uniform cavity is being formed. More uniform means more or less the same depth of cavity is there from the wall of the cavity feature towards the center of the cavity. So, you get a better feature created over here compared to this, unless you are looking for a tapered cavity, and these photographs or these results are taken from the reference number 2 given at the end of the slides. Energy intensity distribution of 500 particles for 0.8 megapascal, again from reference 32. Now, you can see here impact energy on this axis, and this is the center of the nozzle and left side and right side of the nozzle, and you can see here again same parabolic kind of the energy distribution you can see in case of cylindrical nozzle, because this is the center maximum energy you are having and this is the other end of the nozzle minimum energy you are having. So, a kind of parabolic kind of the energy distribution. But in case of level nozzle the energy distribution is comparatively more uniformly distributed. You are not getting here any kind of parabolic kind of distribution, little bit is there, but not that sharp as in this particular case. So, definitely energy distribution will provide you a certain type of the cavity being formed, as I mentioned earlier. It can be something like this, but in this particular case you can have this kind of the cavity. So, there is a difference between this width and this width that you are getting over here, and here less taper, here much more taper is there. So, measured cross section of both blasting profiles, again interesting photograph is there. So, these are the measured cross section you can see here with the help of the instruments they have shown over here. This is again as I showed you in the earlier slide, tapered one like a parabolic kind of the thing that you are getting in case of cylindrical nozzle. This is the erosion depth, it is maximum at the center because you have the maximum energy at the center as we saw in the earlier case, and minimum energy at the sides. So, minimum material removal is there. So, you have this tapered one. Here it is much more uniform and you do not have that kind of the sharp taper, and this is quite wide compared to this particular one, and this kind of the feature you are obtaining in case of level nozzle. So, what I can tell you conclusively that if you are interested in tapered profile you can go for cylindrical nozzle. If you are going for a more or less straight sided profile or feature by abrasive jet micromachining, then it is recommended to go for level nozzle. So, you can see blasting profiles with still nozzle in these two cases, and this is a measured cross section of both blasting profiles. These are the measured cross section. You can see it is comparable with this particular one, and again with level nozzle it is very clearly showing that bottom surface is much wider than the cylindrical nozzle in as compared to level nozzle. So, level nozzle gives better surface or more flat surface at the bottom as compared to cylindrical nozzle. So, these are also taken from reference 32. Now, very interesting slides are there. What are the applications of abrasive jet micromachining process in real life? Some of those applications are mentioned over here. As you can see in this particular picture, these are the various components which have been machined by abrasive jet micromachining, and this includes both macro machining as well as micro machining as long as applications shown over here are concerned. So, trends for shallow depth cut on ceramic materials. If you are interested in shallow depth, you can go this abrasive jet micromachining, because very deep cut you cannot obtain by this particular process because of the process characteristics, because as you go deeper and deeper, the kinetic energy of the abrasive particles keeps on reducing, and when there is a collision of the abrasive particles together, it further reduces. So, its capability to machine deeper goes down. Another thing is trenches for micromedical applications can be easily made with this particular process. They can be micro in size or macro in size. Both types of the trenches can be made for micromedical applications. Reference cavities for pressure sensors can be made again in terms of micro sizes. Then you have through holes for air and chemical flow. Many places you need not a very deep but shallow holes for the flow of air as well as chemicals. So, you can use this particular process. Please note it carefully that if the material is very hard, probably this process may not work. So, you have to be careful while selecting this particular process, that you check the characteristics or the properties of the workpiece material that you are going to machine and the properties of the abrasive particle that you are going to use. Now, if you are machining very hard material, the pressure of the air abrasive jet has to be higher, and all these things you have to take care of. Cavities for mechanical locations also can be made with the help of this. Again, note that very deep cavities you may not be able to make. Removing flash and particle lines from injection molded parts. Injection molded parts, they are having the flashes left over there after molding, or parting lines are also left over there after molding, and you cannot use the part with flash and parting line, and you have to clean them, and for cleaning purposes you can easily use this particular process, and this is very commonly used for cleaning purposes by different industry people. And there you can select a proper combination or proper ratio of air and abrasive particles. Another very important application is deburring, as I mentioned earlier also. Say when you are drilling a hole, say through hole or through hole, say suppose this is a through hole. When you are drilling a through hole like this, then you will find that burrs are left over there, and with the burrs you cannot use this particular part unless you remove these burrs, and these burrs are many times micron in size. So, this particular process, abrasive jet micromachining, has been used to remove these burrs from the drilled hole parts or other parts, and this does not make much difference whether it is a metal or non-metal, just like deburring and polishing. Polishing also can be done with this particular process. However, you cannot get very good surface finish, but reasonably good surface finish you can get, and for plastics, nylon and Teflon components. Cleaning metallic mold cavities which otherwise may be inaccessible. In mold cavities which are made of metal and they are inaccessible, cleaning becomes really difficult. You cannot use the molds unless you clean it. So, for that purpose, inaccessible areas, metallic molds, you can use abrasive jet micromachining process for cleaning purposes. Cutting of thin sectioned fragile components made of glass, ceramics, etc. When you want to cut them into different sizes of the parts from the bigger sheet or bigger plate, then this particular process is also used for that purpose, and that may be for fragile components made of glass, ceramics, etc. Another thing is removing glue and paint from paintings. When you are painting it, some glue, unnecessary glue gets adhered over there, or paint is removed, which is, paint is left over there, which is to be removed. So, for that particular purpose, depending upon what is the material on which paintings are made, if they are hard enough, then you can easily remove glue and paint from those surfaces with the help of this particular process, and that may be leather objects or metal objects also. Another thing is frosting interior surfaces of glass tubes, etching, marking on glass cylinder. This is very important application, frosting, because you know glasses are used as a window glass or other purposes also, and you do not want that people should see on the other side. So, what you can do, you can use this particular process, abrasive jet micromachining, for frosting those glasses with this particular process. Once you machine, you remove the material by this particular process, they become opaque and you cannot see on the other side. So, for this purpose it can be used for frosting of glass tubes or glass plates, etc., and also for marking on glass cylinder and other glass objects. If you want to write the names of the company or whatever marking you want to make, or number of the part, etc., or your figure of your company, then this particular process can be used easily for etching those surfaces made of glass, made of leather, or even softer metals you can use, or ceramics. You can use this particular process for marking purposes also. Then applications of micro accelerometer beams, you can clearly see here interesting application. This cantilever kind of the component can be fabricated by this particular process. This is a 3D component and you can use for fabricating such kind of the components, or the same thing is shown over here with the help of abrasive jet micromachining. And you can see the dimension 4.5 millimeter is here. So, you can see it is just a width of this and thickness of this particular are in millimeter, or some of them may be even in micrometer. If it is in micrometer, then definitely your nozzle is going to be different when the size is in micrometer. So, you have to decide what parameters you should use, what nozzle you should use, and what abrasive particles you should use. So, the cantilever beam in Pyrex glass wafers for inertial sensor applications can be fabricated by this particular AJMM process. You can clearly see over here. Figure A made by a 2-step erosion process. The first step consists of etching through the complete wafer, sensing mass and thick supporting beam, and using a second mask. But he is saying that by using the first step, you first make this particular part like this. You can do it like this in the first step, right? And once you are, and you remove this material, remove this material, remove this material. In the second step, you use the another mask such that you do not remove the material from here, and from rest of the area you remove the material step by step, keeping it bare so that no mask is there, material will be removed. And you have to be careful that dimensions here and dimensions here are different. That means it is a tapered side. So, as well as this is also a tapered side. So, you have to be careful in deciding the material removal rate at different sections and how you are going to put the mask over there. So, all these things have to be looked into carefully. So, using a second mask, that is for these parts, it has locally thinned the cantilever beam for tuning the resonance frequency of this particular device. So, you can see this is very interesting applications of abrasive jet machining process, which can be for macro as well as for micro features or micro components or devices. Such results could be obtained in one single step using a mask size depending upon erosion rate of the AJMM process. Another way to change the geometry of the mask supporting beam resonance frequency is to apply an opaque erosion process. Figure B shows the narrowed supporting beam by two oblique exposures at 45 degree. You can see these angles are also important. You have to maintain these angles because they may be the requirement of the designer where these devices are to be used. Same way you can see the angle over here as well as angle over here. So, these angles have to be maintained and you have to choose proper type of mask as well as proper angle of the air abrasive jet, because then only if it is at the proper angle, then only you can make these tapered surfaces here, here as well as here, otherwise it will not be possible. So, the angle of the jet is also important, including the mask is also important, but angle of the jet is also important to get these tapered surfaces. So, this is a picture of an accelerometer beam realized by in two steps by powder blasting from the two substrate sides. So, this is made in two steps and glass cantilever by a two-step angular powder blasting process from one wafer bridge. So, this is the second one and two steps I have already explained over here. So, you can see that you can obtain it, but as an expert in AJMM process you have to be very careful about selection of different parameters, mask as well as the angle of the jet. Now, this is another interesting applications. Now, see the scale, this is 1 centimeter. So, you have to compare all these things with this particular scale. Matrix of micro E course. Another possible application of the powder blasting technology is the micro structuring of ferrite substrate. Now, this is the ferrite substrate. Figure shows a matrix of 4 mm wide E core structured in 1 millimeter thin ferrite substrate. This is the thin ferrite substrate over here for magnetic device applications like micro transformers. In this case, powder blasting proved to be not only the most appropriate, but also a very fast and cheap way to get such structures. These structures with the help of microplasting have been done very fast and economically also, and this is the ferrite material. Although this is a ferrite material, this means electrically conducting, then you can use other processes also, but they may be little expensive compared to abrasive jet micromachining. You can use there for such kind of the feature creation the processes like electrochemical machining, micromachining, electric discharge micromachining, laser beam micromachining and so on. But their cost is very initial equipment cost is very high and machining cost is also very high. So, from that point of view you can clearly see it is correctly written that it is very fast and comparatively low cost as compared to other well known micromachining processes. So, this is the miniaturized E course microstructure by AJMM in 1 millimeter, and this is the coin capped over here just to thick ferrite substrate for magnetic device application. This is the coin capped over here just to compare the coin with the or these dimensions with this particular coin. Now, applications capillary electrophoresis chips. Now, very interesting applications you can see over here. The device consists of a glass chip which contains a single separation channel as well as an integrated conductivity detection cell. Now, you can clearly see these are the two electrodes shown over here and these are the separation channels. Channels are being made, you can see clearly here separation is there, and these are the detection points and these are the holes or the circular feature created over here. Now, in contrast to most microfluidic glass devices, the channels are not wet etched in hydrofluoric acid, but machined by AJMM, abrasive jet micromachining, which allows the creation of microstructures below 100 micrometer, and additionally makes parallel holes machining at very low cost outside the clean room environment. See, there are certain things which are to be considered, that these devices you can make outside the clean room environment. Clean room environment maintenance is really very expensive. So, if you can make these kind of the micro features in the open air, that will be very low cost, and that is what it is being emphasized over here. And you need not to have non environment friendly fluids like hydrofluoric acids. Here you are using air and abrasive particles. So, this becomes environment friendly process in that sense. So, that only thing that you have to keep in mind, that abrasive particles should not be allowed to go in the environment, otherwise they will harm the operator. So, you can clearly see here this feature made over here. This is the diagram which has been shown over here, but this is the actual made. These are the electrodes you can see over here, and these are the two holes that have been made over here, and these are the separation channels that have been fabricated with the help of abrasive jet micromachining on the glass. So, you can see the size, these are all micron size made features over here, and this is the coin with the help of which it is being compared. So, you can see here the mask layout of the CE chip, two different electrodes designs are incorporated. These are the electrode designs are incorporated over here. This is used the finished CE chip size 9 into 70 millimeter square, separation channel dimensions length 6 centimeter, width 85 micron and depth 22 micron. So, the width of these channels are 85 micron, depth is 22 micron and length is 6 centimeter. So, you can see how nicely they have been able to build the channels of micron dimensions and quite long channels useful for this particular purpose. By controlling the under etching induced by oblique AJMM blasting, millimeter high microstructure in glass can be fabricated with an aspect ratio of 5 to 10, as well as free standing monolithic 100 micrometer wide structures suspended over many millimeters. So, you can clearly see here these are the features created, these are the, you can see micron size cavities are formed over here on these structures, and these are the different features that have been created. Center hole is there in this particular device as per requirements. It is also observed that the flexopolymer resist mask as a good alternative to the metallic contact mask for structures realized at normal incidence. So, what they are suggesting that you can use the polymer type of the mask in place of the metallic mask while removing the material from these components. So, it depends upon what is the material of the component being machined, because according to the hardness and type of the workpiece material you are going to decide the pressure of the air abrasive jet, and pressure of air abrasive jet will decide what kind of mask material you should use. So, depending upon these parameters you can decide cheaper or expensive mask, because mask also should not wear out fast, otherwise you cannot use it again and again. So, you can see scanning electron microscope, that is SEM, of a structure containing 3 suspended glass cantilever beams. So, you can see 1, 2 and 3 suspended glass cantilever beams realized in 2 steps. First, normal jet 90 degree, followed by an oblique jet 50 degree, and this is the first one, and the closure look of the structure, that is closure look of this one, you can have it over here. So, such kind of the 3-dimensional suspended microstructure can also be fabricated with the help of this particular AJMM process. Now, this is again interesting thing, we have seen this kind of the picture earlier also, earlier slides. Let us see 3D passive glass micromixture. Micromixture are very important in microfluidics, but the fabrication of these micromixture is also equally important. You can use different kind of the advanced mechanical type of micromachining processes, thermal type of micromachining processes, and chemical electrochemical type of micromachining processes, depending upon on what material you want to make these micro mixers. If you are going to make on glass, then you have to use advanced mechanical type of micromachining processes, and abrasive jet micromachining is one of them. A passive micromixer with 3-dimensional features fabricated by abrasive jet micromachining by implying photopolymer. Photopolymer is used over here as a mask, because we have seen different kind of the polymers in the last lecture, that were metallic, elastomers and photoresist polymers as a mask on a glass slide target, as shown over here in figures A, B, C. Now, this is the coin, and this is the glass on which this micromixer has been fabricated. The mask using SU8, a photosensitive polymer, is applied as a micro pattern for abrasive jet micromachining. So, photosensitive polymer is used, and the mask is made of SU8. We have already seen SU8 application as a mask. Fabrication process involved 3 glass target slides and conducted multi-masking processes with 4 different mask patterns. The fabricated proposed micromixture had an overall length of 13 millimeter and a width of 2.5 millimeter. So, you can see this is the width which is mentioned as 2.5 millimeter, and this is the length which is mentioned as 13 millimeter. And so, definitely it is a micron size mixture or channels which have been fabricated over here. The micro channels had a semicircular shape with an average width of 350 micrometer and an average depth of 150 micrometer. This is very important. Semicircular shape of the microchannel, it is not easy to make semicircular shape microchannel, as I will show you. As you can see here, this is the another view. As you will see, 3 glass layers were successfully bonded in a single step using a direct bonding method. So, you can see 3D spring like micromixture comparison with 1 cent coin. This is the 1 cent coin which is very small in size. So, this particular mixture base material or plate has been compared with that particular coin. Side view, this is the side view of the micromixture. If you take the side view of this micromixture over here, then you will find that it will look like this. This is the top part and this is the sectioned part of this particular mixer. Now, you can clearly see it is a tapered one, mixing fluids are there, here the fluids will be mixed over there, and this is the cross sectional view of this particular one. So, you can clearly see this is the kind of the channel that has been cut over there, and this is the another cross section of the channel. So, you can clearly see what kind of features you can create with the help of this or micro level. So, this is the comparison of the 1 cent coin and micro mixer plate, and this is the side view of that particular one, and this is the cross sectional view. What are the advantages? Here in this particular case you need minimal tooling cost, because you do not need any tooling except that you have to use the mask, and mask itself is a tooling. So, the cost is minimal except in very special cases when you are going to micron size, you have to make it with special processes those particular mass. Another thing is quick turn around for prototyping and development work. That means you can quickly make the devices prototype, so that before you go really for mass production or production, if you want to test those devices, then you can use this particular process to make the prototype, test it, and once it is working, then only you can go for production, and in production you can definitely use different kind of the processes which give minimum cost and the desirable production rate. Feature size is down to 100 micrometer and feature depth to just a few micron are possible with this particular process that we have seen. In some cases, feature location and dimensional tolerance is down to plus minus 25 micrometers are possible. And second thing is, even in inaccessible areas, if the jet can go there, it can do the machining operation, which is not possible otherwise also, except very few advanced machining processes. So, this is the additional advantage of this particular process, that small features and in inaccessible areas also you can make those features with the help of this particular process. Another thing is, multiple features can be machined in one operation and very high pattern densities are possible, because here it depends upon what is your pressure, what is the feed rate, and what is the size of the abrasive particle and pressure. So, you can choose high patterning rate by this particular process by controlling these input parameters appropriately. Features can be of any 2D shape like square, round, designed shapes and connected channels. You can have different kind of the features created over here, because you have to have proper relative motion between the workpiece and the jet. If the jet is moving like this, which you can really control by the numerical control devices, NC machines kind of the feature, machines kind of the characteristics of the abrasive jet micromachining, you can have relative motion between the workpiece and the air abrasive jet, and you can create all kind of the features like square, round, or any shape that you can design, or parabolic, whatsoever you are interested in, you can, or triangular one, you can connect the channels. And masks are made directly out of CAD. For making the mask, as I mentioned earlier, computer aided design can be used, CAD files can be used, reducing the risk of pattern error. All this can be done on the CNC machines also, where you can directly cut the metallic parts, or even non-metallic parts can be cut on the CNC machine using the CAD file, and they can directly give you very nice patterns. The process generates no heat, because here heat generation is minimal one, because you are using the kinetic energy of the abrasive particles, and abrasive particles are shearing or making the brittle fracture. So, some heat is generated, but you can say it is almost no heat, because this is the comparison with the traditional machining processes where the temperature of the workpiece and the tool goes 500, 600 degrees centigrade. Here the rise in the temperature may be in 10s or 20 degrees centigrade, not more than that. That is why it is mentioned that no heat is generated, however theoretically it is not a correct one, but practically it is a correct statement, and it does not change the material properties of the workpiece. Increasing the temperature of the workpiece by 10-20 degrees centigrade has no effect on the properties of the workpiece material, but in conventional machining processes where temperature goes up to 500-600 degrees centigrade, definitely there are the changes in the mechanical and physical properties of the workpiece, but not in abrasive jet micromachining process. And the process works well with metallized parts also can be machined with this particular process. There are certain limitations of this particular process, as with every other processes also they have the limitations. Unlike vertical side walls produced by ultrasonic machining, we will discuss ultrasonic machining later, where you can get more or less vertical side walls, that means taper of the side walls is very small. Abrasive blasting machine features have tapered sidewalls. I have already shown to you that you are going to get tapered cavity or tapered sidewall, whatever feature you are creating, and all this, because abrasive air jet has a flaring characteristic. As the stand of distance increases, flaring of the jet increases. Hence, you cannot avoid the taper in the machining feature. However, to certain depth you can avoid, minimize it by having minimal possible stand of distance or nozzle tip distance, ranging from 18 to 26 degree as the taper angle, depending on several factors, basically input parameters, and also the characteristics of the workpiece material. Maximum aspect ratio is 3:1, that is the depends upon the thickness and your input parameters. And then applications are restricted to brittle materials because of low MRR in case of ductile material. Definitely in case of ductile material you are going to get very small MRR, because abrasive particles itself may get embedded into the ductile material, and when you are forcing other abrasive particles, they may be breaking the embedded abrasive particles, and definitely your material removal rate from the workpiece is going to be low. Sometime additional cleaning operation is required to machine parts to remove abrasive from the surface, because many abrasive particles may remain there on the machine surface as embedded abrasive particles, or they may get adhere to a very small thickness. So, you have to remove all these particles before really you can put this device into use or in assembly. This is very important part, you have to be careful. Machining accuracy is comparatively poor. When we are talking of machining accuracy, definitely we are talking of the dimensional accuracy of the part as well as geometrical accuracy of the part, and both may be comparatively low, but there are many hundreds of applications where you can use abrasive jet micromachining where you do not need very high accuracy also. Nozzle wear rate is high, as I mentioned earlier. Nozzle is subjected to abrasive particles when abrasive air jet is coming out, and so depending upon the nozzle material and the pressure and the abrasive particle characteristics, nozzle wear rate is decided, and once it goes beyond the dimensional tolerances, the wear you must replace before that particular incidence happens, or you start rejecting the part. And then the process tends to pollute the environment to some extent. I have already mentioned that you should use the hood so that abrasive particles are not allowed to get suspended in the environment, otherwise it is going to be non-environment friendly process. Also it is going to harm the people working around the machine. So, this is another very important thing. I have mentioned to you in between again and again different references. First reference, as I mentioned, that T.J. Coe, he has written a chapter on abrasive jet micromachining in the book on Introduction to Micromachining, published by Navasa Publishing House, New Delhi. Second reference which I have given there is Goviti et al. Process repeatability in abrasive jet micromachining, Journal of Materials Processing Technology. It is PROCESSING, spelling is not correct, and 190 volume 2007, 5160 page number. Third reference is Ext Nick et al. It is a very good paper, Modeling and Evaluation of Micro Abrasive Blasting Process, published in the International Journal Where, 259 volume in the year 2005, 8494. And then next reference number 16, Ext Nick et al. And the title is Erosion Behavior and Pattern Transfer Accuracy of Protecting Mask for Micro Abrasive Blasting. It is again published in Journal of Material Processing Technology, 149 volume 2004 year, 4349. Again A. Goviti et al. Process repeatability in abrasive jet micromachining, Journal of Material Processing Technology, in volume 190 2007 year, 5160 page number. And the last one, 32 reference, is again Act SNCC, Modeling and Evaluation of the Microabrasive Blasting Process, where 259, it has been repeated because I have already mentioned this over here, that is the in reference. So, these are the references which I have, from where I have used some of the figures. So, I thank all these people for this particular one. Now, there is a problem based on whatever we have discussed so far. I will just read it. A glass specimen, this is the numerical problem. Such kind of the problems may be asked to you in the examination, and in real life also you may use this kind of the problems for analyzing the process. Now, let us discuss one numerical problem based on the abrasive jet micromachining. A glass specimen is covered by metal mask with thickness of 100 micrometer and a hole pattern of 80 micrometer diameter. The specimen is a soda lime glass slide with size of 250 into 250 into 1.2 millimeter cube. The air pressure of 2 megapascal gives a jet stream velocity of 150 meter per second. The AJMM system used alumina as abrasive particles and set the feed rate at 0.02 gram per second. Now, please note it carefully, it is 0.02 gram per second is the feed rate of the abrasive particles. How long would it take to get a through micro hole? Now, let us try to find out this with the help of equation 1, which we have already discussed. Principal mass loss of the erodent is proportional to the amount of abrasive. This is what the assumption is, and based on this that equation is derived, and it is true for most of the brittle materials erosion, and we are discussing here the glass, soda lime glass, which is also brittle material. Hence, this equation 1 can be applied for, where if you recall, you can go back and see that equation, and where K is the dimensionless factor, m is equal to the amount of particles units kg, v is the velocity of particles, that is abrasive particles in meter per second, rho is the density of eroded material. This eroded material is the workpiece material density, and the density is given as kg, that is kilogram per cubic meter. H is the hardness of the eroded material, that is the workpiece, in terms of kilogram per millimeter square. From the above, now let us try to find the solution. From the above problem and standard, the soda lime glass is brittle material, that we already know. Erodent is alumina, abrasive particles, eroded material is workpiece material, that is glass, which is not written here. Abrasive feed rate is 0.02 gram per second, that is equal to 2 into 10 raised to power minus 5 kilogram per second, and gravity that we all know already is 9.8 meter per second square. Now, density of alumina 3.95 gram per cubic centimeter, which comes out to be 3950 kilogram per cubic meter. This is cubic meter, m raised to power 3. And then density of soda lime glass, that is the workpiece material or the eroded material, that is 2.5 gram per cubic centimeter, and which is 2500 kilogram per cubic meter. And then you have density of, you have hardness of soda lime glass 585 kilogram per millimeter square. So, this comes out to be 586 into 10 raised to power 6 kilogram per meter square. So, you can write it like this, 586 into 10 raised to power 6 kg per meter square. And then you have the velocity of abrasive particles which are coming out of the air abrasive jet, 150 meter per second, hole diameter, that is 80 micrometer, this is micrometer, like this, and height is of the specimen is 1.2 millimeter, that is equal to 1200 micrometer. K is the constant as mentioned earlier, it is taken as 2.3, and diameter is 80 micrometer, thickness is 1200 micrometer, soda lime glass. The mask being used is metal mask, as we have already seen 3 different kind of the mask can be used depending upon the requirement, and volume of the hole which is to be machined, which is equal to pi r square, that gives the cross section, and h is the depth, pi r square h. So, if you substitute the values from above, 3.14 is the value of the pi, 40 micrometer is the radius, that is r square, micrometer square, into 1200 is the depth up to which it will be machined, because you can see here this is the height of the specimen or depth up to which the hole is to be drilled, that is 1200 micrometer. You can simplify it, it comes out to be 6.03 into 10 raised to power minus 12 cubic meter as the volume of the hole to be machined, and mass of the abrasive particles is equal to nothing but volume of the hole multiplied by density of the abrasive particle. So, you get it like 6.03 into 10 raised to power minus 12 cubic meter into multiplied by 3950 kg per cubic meter. So, you simplify it, you will get 23.73 into 10 raised to power minus 9 kilogram. Now, this is the kind of the machining you are going to do. This is the metal mask, this is the soda lime glass plate, and this is the thickness of the plate to be machined as the 1200 micrometer, and this is the thickness of the mask that has been put over this soda lime glass plate, and this is the hole to be drilled which diameter of the hole is 80 micrometer. So, this is the kinds of the structure you are going to fabricate with the help of abrasive jet micromachining. Now, volume of the hole we have seen it 6.03 into 10 raised to power minus 12, which is pi r square h, r is the radius of this and h is the height 1200 micrometer over here. So, volume, and this is the mass of the abrasive particles, that is the volume of the hole into alumina, that comes out to be 23.73 into 10 raised to power minus 9 kilogram. So, what is going to be the weight loss? We have already seen this equation 1, with the help of which you can calculate the weight loss, and this is given by K into rho divided by H for soda lime glass into half m into V square, that is the V is the velocity, m is the mass of the abrasive particles. So, this is for abrasive particles, this is for the workpiece material, that is soda lime glass. So, as we have already done and we have already seen the values of these different parameters, you substitute these values of different parameters, you will get 3.36 into 10 raised to power minus 9 kilogram meter per second square, right, that is the weight loss. So, weight loss is nothing but m into g, g is the acceleration due to gravity, m is the mass. So, weight loss is equal to mass of the workpiece material to be eroded is bit loss divided by G. So, you divide this value 3.36 into 10 raised to power minus 9 by G, then you will get 0.34 into 10 raised to power minus 9 kilogram. So, please be very careful about the units of every parameter, otherwise you will not get the correct answer. So, you get it, T is equal to mass into feed rate, this is the mass of the abrasive particle feed rate, you will get like this. So, you will get it, the final answer as 0.258 into 10 raised to power minus 4 seconds. So, very quickly you can machine this hole if you follow these parameters as I have just mentioned. So, like this you can have many problems for abrasive jet micromachining as long as numerical problems are concerned. Some problems as descriptive problems are given in the book in the chapter which I told you in the beginning, which has been written by Professor Ko. So, thank you very much for listening this particular part of abrasive jet micromachining. Thank you.